Very pleased today to introduce to you Professor Herbert Wilf from the University of Pennsylvania, who's, to our good fortune, spending his sabbatical year at Stanford this year. Herb.
Good afternoon. I'll try sitting down for a bit and see how that works. I think this is a marvelous kind of course. I could have used it when I was at your stage of my career. It would have saved me and the world some grief, mostly me, if I had a little training in it. At the moment, I guess my main contact with mathematical writing, that is, in addition to what a mathematician would normally have, comes from the fact that I'm editing two journals, and they're very different journals. One of them is the American Mathematical Monthly. Now, the monthly is an expository journal. If you have just found a proof of some new and important result, normally you would not send it to the monthly. You would send it to a research journal in that particular specialty. Although, may I say, that does not seem to be the case with proofs of Fermat's last theorem, in which there were quotation marks around that word proofs. In fact, I just got one yesterday. By the way, I had trouble working out a policy. In fact, I still have trouble with proofs of Fermat's theorem. What should I do? After the first 15 or 20 of them, I made up a form letter that I thought would hurt as few feelings as possible, because the objective is, not to have to worry about it if it's not a right proof, but not to hurt people. So I tried for a while saying that this is not a research journal, and you have claimed the proof of a very important theorem, and you should send it to a journal. So I started getting poison pen letters from editors of other journals, of course. And I'm not quite sure what to do. Was there a comment somewhere? Okay.
Who would you rather hurt?
Right, that's it. Well, and of course the other point is, sometime, somewhere, somebody will prove or disprove Fermat's last theorem. That's just an act of faith in saying that, but I think it will happen. And they all, sorry?
So then the editor of the journal will send it back with a snotty letter.
Yeah, well, I don't want to send any snotty letters. And this last one, I don't know, it goes with the phases of the moon. The one I got a couple of days ago, I just sat down and read it all very carefully, all the way through to the end myself, and found the mistake on the last page and sent it back. But someday. Anyway, so one journal that I'm the editor of prizes mathematical exposition. That's what it's about, as opposed to research papers. The other journal, of which I am one of the editors, was founded by Dr. Knuth and myself in the year 1980, so it's about 8 years old now, and that's the Journal of Algorithms, and that is a research journal in guess what specialty? That's right, algorithms. So the criteria for what makes a good paper are different in those two journals. What makes a good paper in the Journal of Algorithms has a lot more of, is this a new result? Is it an important result? Does it contribute a lot to the field? And if that's true, then you can forgive all sorts of, lapses in style of expression and other things that the other inadequacies of the author or authors in writing it up. On the other hand, for the monthly, one really wants to have very lucid exposition. You want to see where you're coming from and where you're going, so you can decide whether to make the trip with the author or not pretty early on. I guess the way I feel about it personally is, so I have lots of experience in reading mathematical articles of both kinds, supposedly evaluating them intelligently, supposedly, and stuff, but somehow I just feel older without feeling wiser. That is, I wish I had a lot more to communicate with you in the way of rules and stuff. I have a little list here we can talk about. I don't know that if you'll hear a whole lot that's new on it, but maybe we can talk about it from another angle. The point is that mathematical writing is a very human interaction. It's a human interaction. It's between one human being and another human being. Depending on whether it's expository or research, it may involve the brain more than the hormone system, or the hormone system more than the brain. Okay, they're both involved. It's a complex human interaction. And who knows, who among us knows how to make rules of human interactions? It's just about as complicated as it can be. So but we can toss little remarks out and see what happens. I guess the first story that came to my mind, I think I'd rather not suppress this one, I'll just tell it, was in the year 1966, and it's about my son Peter. We were in Paris on a family vacation, and Peter was 3 years old, and we had a wonderful time, and from time to time we had to take a taxi to get from A to B in Paris. And so, of course, we all know how to take taxis. You stand out in the street, you hold your hand up, a taxi stops, and everybody gets in it and goes off where they're going. Well, Peter was fascinated. He was 3-year-old, and he was delighted with the fact that just by stepping out in the street and holding up your hand, you could stop traffic and get in and go on. So I noticed that he was studying very carefully exactly how I did that. And one day he tried it. He stepped off the curb and he held his hand up like this. And of course he was about that high, you know. And the Paris taxi driver would no sooner have stopped for him than gone to the moon. And they all went zipping right past, of course, ignoring the little child with his hand in the air. And I didn't say a word. So what his reaction to that was that the next few times I raised my hand to stop a taxi, I saw him looking at me extremely intently, and he was tipping his head, and he was watching the angle, and if I had my finger up like this, he was practicing holding his finger exactly that way. He was sure that there was some little secret there that he could learn from. Of course, he never stopped any taxis. So to a certain extent here, one can watch, for example, how Dr. Knuth holds his hand up in the air and whether he has his finger up, but it's unreasonable to expect as many taxis to stop, you know, for some of us as for some other people. It's it's like that. Nevertheless, we can study. Okay, next thing I have, sorry, any comments so far? Okay. Next reminder I have for myself is how it's important to get the attention of the reader more or less immediately. I'm now concentrating, may I say, on the exposition part of things. The content is really, you know, the thing that distinguishes the 3-year-old boy from the adult who's trying to stop the taxi. It's the content. That's the important thing. But from the expository point of view, if you want to get you want to get the attention of the reader immediately. How can you do that? Well, you can say what it is you are going to do or try to do in that paper and say it very close to the beginning. Just get it right up front. In this paper, we will prove Fermat's last theorem. I mean, that really stops traffic, okay? Just get it right up there. You don't say we will consider certain Diophantine equations in the theory of whatever, p-adic forms or something. We are going to prove, okay. Let me read you a couple of examples of how some people have done that. Here's a paper by, I see it on the screen now, okay? Here's a paper, I also see that when I come to an example that I'm using as a negative example, I better be careful to cover up the author's name before I lay it down in front of me. This, however, is one of my positive examples, so let's let it sit there. Live and learn. The TV scene is very complex. Okay, so this is called How I Became a Torchbearer for Matrix Theory. And it's by Olga Taussky-Todd at Caltech, who is certainly one of the distinguished ladies of American mathematics. She is a very fine human being, and she has proved many very important results in the theory of integer matrices, for example, in spectral theory, in inequalities, and all over the lot. And now she's beginning to write a little bit about, you know, what her career seems like as she looks back over it as a senior mathematician. In any event, here's the first couple of paragraphs. Some time ago, I picked up a book, The Best of All Possible Worlds, in our public library by Peter Drucker, a professor of social science at Claremont Graduate School. On pages 91 and 2, Drucker writes about a man, Hinton, a pupil of Riemann. Hinton was to write a thesis on quaternions. Riemann saw their importance to his own areas to lead to new results in what now, Hinton thought, they call matrix algebra, which has become all the rage. But matrices were not always the rage. They have played a big role in group theory since Élie Cartan. They play a role in physics and in statistics. But matrix theory on its own reached me only slowly. My main subject being number theory, I did not look for matrix theory. It somehow looked for me. In what follows, a number of such events are sketched. I think that's a really nice way of saying what it is that's going to happen. This is a biographical note that you're about to read. It's about how someone gradually became attached to a certain subject, or maybe it sounds like the subject became attached to her, the way she puts it. And that's what it is. It's biographical. It's how she happened to be led into, by a mysterious force, this and that gorgeous theorem that she found in the course of looking into matrices. So this certainly, in my opinion anyway, satisfies the condition of getting one's attention in a really nice way. Any comments on any of that? Okay. I brought along another paper, which is kind of nice. In fact, this got one of my colleagues' attention so thoroughly that his reaction instantly was that it's wrong. And so we are checking it to make sure that it's right. But I think it's right. Anyway, it's very compelling, I think. Can a graph be both continuous and discontinuous, is the question by Thurston. The title means, of course, can one and the same set of points be both the graph of a continuous function and the graph of a discontinuous function? So let's think about that for just a moment. I'm going to interrupt the reading of it. So imagine that there's the xy plane sitting in front of you, and there's a certain set of dots sitting in the xy plane. Okay, so that's somebody's graph. Now the question that he's asking here is, suppose I draw the axes this way, y-axis here and x-axis here, and I consider that to be the graph of a function, what I have there. And suppose that's a discontinuous function. Now, is it possible that if I draw my x-axis and y-axis at some other, still at 90 degrees to each other, but in some other orientation in the plane, and look at that, I will still find that it's a graph, which means that it's still single-valued over every x. There's one value. Okay. But now I find that it's the graph of a continuous function. So can the very same set of points sitting there in the xy plane be one and the same time the graph of a continuous function and a discontinuous function? Let's see, if S is a set of points in a plane, and we can set up axes in such a way that no 2 points of S are in the same vertical line, then S is the graph of some function. If we can do this in 2 ways, S is the graph of 2 functions. The question is then, can one of these functions be continuous and the other discontinuous? The answer is yes. Let us start by quoting the definition of continuity, etc. Okay? Now, I find that a compelling beginning for a piece of mathematical writing. I am interested in that question. He has said it, I think, very lucidly, what it is that I should be interested in. Of course, it's my right not to find it interesting. I happen to find it interesting, but at least he's got it all up front. You see exactly what's inside the package that you're about to open, and it's up to you whether you want to open it or not. Okay, but it's all right there. Okay, it turns out to depend on whether the set of points is compact or not, whether the domain of definition of the function is a compact set or not. If it's a compact set, then the answer is no. But if you allow it not to be compact, the answer could be yes, is what it comes down to. Okay. There's one other piece of advice that I have here that I'll ask you to follow, and I hope that you all will follow it. If you want people to read the things that you write, be famous. It helps, really. As an illustration of that, I want you to promise me now, please, that you will all end up famous, and I wish that it happens. And here's a paper whose title I'm not quite sure that I can read, but I will try. Angle trisection, the heptagon, and the triskaidekagon. It's that last word that I don't quite trust myself on. And it's by Andrew M. Gleason, Department of Mathematics, Harvard University, and he's famous. Okay, not only that, justifiably so. He's a brilliant fellow who solved Hilbert's nth problem for some n many years ago. Okay, so now there are only capital N minus 1 of Hilbert's problems left, and he was finished. And he has since written on many, many subjects very beautifully and very substantively and compellingly. Okay, so he writes well, and he proves very important stuff. So when you see a paper that's by him, it's another form of grabbing your attention in the first paragraph. It's another way to do it. Okay, there are lots of ways to do it. That's one way. So when he writes a paper, the first paragraph is not that important. The title page was really important already. Okay, so do be famous. This is a really nice article, too. These are all coming out in the monthly someday. I'm trying to sell monthlies, of course. That's part of my job. So I hope you will all run down to your newsstand and read about that. Fame has its price is the next subject that I wanted to speak about briefly. That is, if everybody knows who you are, for example, then one little problem that you might have is that it's hard to get your papers refereed. Okay? So I wanted to tell a little story on your professor that happened some years back along that line, which may have come up already in class, but let me try it anyway. He submitted a paper to the Journal of Algorithms a few years ago, and he wanted to make sure that it would get a really careful and impartial refereeing without regard to the fact that he was one of the editors-in-chief and founders of the journal and so forth. And so he asked if I would respect his confidence, if he would submit it under a nom de plume. The name that he used, in fact, was Ursula N. Owens on that particular paper. And we had it refereed that way. The referees loved it. It was, accepted for publication and so forth. And I can understand all that fully. And I wanted to show you the bottom line if I brought it. Where did it go? Excuse me, there's a bottom. Oh, here it is. After the whole transaction was complete and the paper had been published, I got this letter from Dr. Knuth, which says, dear Herb, thank you for your patience and kindness in the editing of this paper. I think it's now ready to go into your backlog instead of mine. Sincerely, Ursula N. Owens. And it has this. Okay. So, you can't escape these things once you do them.
He sent me a dozen roses.
I can't escape either. Okay. Great. I shudder to ask the next question. Are there any comments about that? Okay. A little more seriously, I was kind of interested in how this turned out in myself. The next thing I asked myself was, I'd like to tell you a few mathematical books or whatever that I found to be particularly well written. So they were really memorable, really fine examples. And I wrote down 3 examples, and I kind of amazed myself. In other words, first of all, I'm not kidding in the sense that these are 3 of the books that I use really very, very often. Excuse me, I should say that this discussion is going to take place present company excluded, okay? Dr. Knuth's 3 volumes are absolutely on anybody's list, right? But no fair, it's his class, so let's talk about other company, other people. But these 3 books, well, let me give you their names first of all. Number 1 is the book by Pólya, Szeg. Those were, in fact, 2 distinguished Hungarian mathematicians who spent their latter years at Stanford and have passed away only fairly recently. Both of them well into their 90s, in fact. Pólya and Szeg, yes, you see them here. And the title of the book, well, as they originally wrote it, it was Aufgaben und Lehrsätze aus der Analysis, and as it became in the last 15 years, Problems and Theorems from Analysis. Problems and Theorems from Analysis. And that's in 2 volumes. And the book was written, I don't have the exact date, but I would guess it's 1920-ish. I'm not quite sure. And let me say some of the things about that I find to be quite remarkable. Well, I guess, just very personally, the reason it's on my list is that I refer to the thing all the time. I'm just always there looking up things. Okay, it's just stayed with me consistently. The format of the book is that there's a problem section and there's a solution section. Okay, the problem section is divided up according to the field of analysis that's being talked about: power series, complex functions. It's mostly an analysis of various types, as the title suggests: theory of numbers, conformal mapping, and so forth. Different topics in analysis. So there are problems in each one of those sections. The problems are individually self-contained, so you need rather minimal interconnection with the other problems to understand the question in a particular problem that you happen to be looking at. They're quite nicely self-contained, and that's part of the artistry of the thing, is how self-contained or how self-containedly they have stated those problems. So you don't need to go chasing back to a whole lot of previous stuff to see what the question means. Okay, that's really very well done. And furthermore, each one of the sections has the property that there are several major themes that are being developed. And if you look at, for example, problem number 5, 15, 17, 23, 38, and 49, in that order, it turns out you will have proved for yourself a major theorem in that particular part of the subject. So somehow major results and major ideas are being broken down into smallish, bite-sized pieces and little problems that are themselves self-contained. And the answers are given in the second half of the book. Well, they're quasi-answers. Sometimes they'll say, all you have to do is look at number 13 in chapter 2 and number 17 in chapter 9, period. That's all it will say for the answer. And then you go look at those two problems and you sit there scratching your head for the rest of the day because it's not quite clear what you do next. So they're answers, but they're spare. They're on the spare side. Okay. The book, I think, I think I have a lot of company in that. This is scarcely an original opinion. This is a very widely admired and respected pair of books from a widely admired and respected pair of people. I think that, in fact, that Szeg was Pólya's student in Hungary, doctoral student. Okay, and the second book on this little list is by Hardy and Wright, and it's The Theory of Numbers. That's a book with a lot of limitations in the sense that it's short on one of the things I wanted to talk with you about a little later on, which is motivation. It's a, what's it like? It has like a jewel-like crystalline structure to it. The theorems are stated very precisely and concisely, and they are proved very precisely and concisely. Okay? And then they're off on the next topic with some perhaps literate or whatever connective kind of comment between them. It's not just a sequence of disjoint statements by any means. There's strong connective tissue there. But the statements and the proofs of the theorem are really lean and mean, okay, in which you sort of have to work your way through them, like very carefully. I think I would like to quote for you as nearly as I remember it. I'm sure I remember the spirit of the comment, something out of their preface, which is relevant to this class. In their preface, which again I cordially invite you to read in full, the preface of this thing, they say the following. They say that we have tried to do thus and so with the theory of numbers in this book. We may have succeeded, or we may have failed. We cannot have failed completely, however, the intrinsic beauty of the subject matter being so great as that only extravagant incompetence could make it dull. Okay? That's almost a quotation from their introduction. So that's another weapon that you have, along with fame and whatever, in writing good mathematical writing. Namely, it's to write about things that are intrinsically very beautiful, okay, and show that you respect the beauty and that you are trying very hard to convey it to other people. As I say, when I wrote down this little list of 3 books, I was kind of surprised at myself at how they turned out, because the 3 of them share this very spare style that I've just been commenting on. And in my own style, as I was going to tell you also somewhere in here, that has been loosening up over the years. I find myself getting more chatty and talking more around things instead of directly at them. Okay, and I'm not at all sure that's right or wrong, but I find myself admiring these 3 things, which are, as I say, extremely spare in their mathematical style, and do not talk around things at all. They just say them and go on to the next thing. Whatever. One more contradiction in life. What else is new? The 3rd book on this list is absolutely a model of mathematical sparsity. Okay? If a word can be left out of Rudin's mathematical analysis, then he has left it out. He has, in fact, left out several words that couldn't be left out. I have, in fact, taken this as a course from him once upon a time, a great many years ago, and it knocked me for a loop. In the beginning, there was a period of, what this is an introduction to rigorous mathematical analysis, as opposed to freshman calculus. There's freshman calculus and sophomore calculus where the emphasis is on how to do this. And then somewhere, if you're a mathematics major or a professional mathematician, at some point there will be a crunch in which you take a course where you have to prove everything that you say precisely for the first time. That can be traumatic. There can be books that ease the trauma, and there can be books that make it worse. This one made it much worse. The amount of motivation in here is 0, except for one little detail. By the time you get to the end of it, if you're still alive, you feel very strong indeed. Really. And that's some kind of motivation. It's just that it happens afterwards instead of before. Okay? Now, that's not really motivation as one normally thinks about it. That kind should really come first. He doesn't give you a crumb, just nothing. But it's a gorgeous style. I mean, for example, when you start seeing statements like, if you're a junior in mathematics, knowing from nothing except for freshman and sophomore calculus, and you see someone saying, since the series is uniformly convergent, there is a capital N such that for a little n larger than capital N, all terms are less than epsilon over 6 capital M squared. Okay? Now the epsilon was hard enough for me to swallow, but where did he get the 6 capital M squared in the denominator? Well, after you've been through 50 of those, you know that the reason is because it comes out right at the end. Everything turns out to be less than 1 times epsilon, and that's what you were trying to prove. And it's not good style to have it turn out to be less than a half epsilon or less than 3 epsilon all the way at the end. So if you make a proof in which the bottom line is that it's less than 3 epsilon, you go back all the way back through the proof and divide your whole argument by 3, so it turns out to be less than epsilon. That's the reason. Okay, but this is really hard on the young, let me tell you. But that is one beautiful book. Okay, it's a gorgeous book. You really learn how to prove things, and you learn what isn't a proof. Okay, you learn what isn't a proof, and you learn what is a proof. Okay, they're all very dry in their style, all 3 of them. Okay, comments? Anybody wish to? Yes, please.
I trust you don't learn what isn't a proof by example.
No, there are no, well, you could learn, one could imagine that books like that could exist, and indeed that they could be quite interesting if well done. I don't know of one offhand, and one doesn't want to overdo that kind of thing. But certainly, well, in fact, I can think of a few books now that have things, non-proofs sitting in them with challenges to the reader. Can you find the flaw in the following proof of Fermat's last theorem, the 3-color theorem, or whatever? So one can certainly do that, and it could be instructive. Other comments? But
you said dry, but somehow that doesn't, I don't get a feeling of dryness from it. It's because the things are so well chosen that the writing would be dry if you were comparing it to a poem or something, or written for someone who wasn't already motivated. But it carries the motivation through by the beauty of the arguments and the way they flow.
indeed. Thank you. My dry comment really applied primarily to Rudin. The other 2 are not really. They're lean, but okay. You said it. Any other comments? Thank you. Okay. Let me toss in a small random remark that has to do with just a personal comment about my own feelings about my own style. My perception is that when I was much younger, just starting out as a mathematician, that I didn't have a whole lot of personal security and personal self-esteem. My self-esteem was not very good. It was about the square root of -3, as I remember. And, there's no way to get that larger except by feeding it good, solid food of theorems that you have proved, or, if that's your goal, or algorithms that you have developed or analyzed, or whatever you set for yourself as your professional goal. Doing it is the very best way to raise your self-esteem. There's no good substitute for it. Anyway, this is personal. I really can't claim to be giving universal advice. But at that time, when my self-esteem was not so hot, I found, or I see now from looking at what I wrote at that time, that I tended to stick pretty well to established forms in the way I wrote about things. I sort of wanted to find somebody else who was writing about similar things and stick to it as close as possible. I wanted to fit into a pre-existing framework because I didn't have a lot of personal security, and I didn't feel free to bust out of all that. Okay. Now I feel a little better about myself, just partly from having done 1 or 2 things, and partly from having noticed that almost everybody else in the world shares those feelings of inadequacy that I had at the time, and the combination of all that just has made me feel better. And so I feel a little better about loosening, the screws on the style. And so I tend to develop my own style, I guess. I guess that's all it is, really. I've developed my own style. It's a little chattier than I was back then. I talk around things. Well, you'll see, but from the handouts, which I'll discuss presently, there's a couple of examples of my style. I say to myself that the way I like to write now is to be a little bit chatty before I get down to the nitty-gritty, and then when the time comes to prove a theorem, to try to do it the way Rudin would have done it, and then put the QED sign, and then try to chat a little bit more. But somehow when the crunch comes, you want to stop chatting, and you really want to do what has to be done and clear out. Any other remarks at this point? Okay. Let me mention motivation again, because that's really one of the important subjects.
I've got one question about what
Sure.
you just said. Would you say then that the right thing to do for us who are just starting out is to stick with established forms, or would you say be confident and try new things?
I certainly wouldn't phrase it as be confident. My own experience is, as I say, that can only come after you have met Mother Nature and found one or two of her secrets. Just one or two is enough. It doesn't have to be 50. So I don't know. I find it really hard to begin a sentence by saying you should do X. I feel much more comfortable saying it seems that I have done X now that I'm here.
I was just wondering if you were saying you were wrong to have stuck with the forms when you were younger, or if maybe all along you should have.
No, he was an okay guy too. I'm reminded of a lecture by I.J. Schoenberg, a very distinguished mathematician now at the University of Wisconsin, having retired. And he gave a colloquium talk at the University of Pennsylvania in the 1960s, as I recall. And he began it by saying, I was reading the work of a younger mathematician on the following subject, and it was about the Kakiya's problem, which is the turning a needle around. You want to turn a needle around in the plane so that it's 180 degrees from where it used to be. And you want to do it by sweeping out the smallest possible area while you're doing the turning. And the question is, what is the smallest possible area of the plane that you can sweep out if you take a needle of unit length and you want to reverse its direction, okay, like that. And so that's the Kakiya problem. The answer turns out to be epsilon for every epsilon. You can do it in less than, for every epsilon, you can do it in less than epsilon area. That's it. Anyway, so Schoenberg began by saying, I was reading the work of a younger mathematician, and he was 26 years old, in fact. And you know how younger mathematicians are. They're full of energy and brilliance and so on and so forth. But they often don't see the implications of their results and the connections with other fields and so on. He says, now I'd like to interpret that for you and tell you what that's all about. And after 3 more sentences, it developed, of course, that the younger mathematician he was talking about was himself of 20 years ago, meaning that he had written up something and he had not seen any of the implications or anything, but he sure had proved that theorem. And now, 20 years later, he wanted to tell us how it fitted into the rest of mathematics in a kind of more relaxed way. So I guess something that's common to a whole lot of mathematical styles. Oh my goodness, is this almost over? No, it isn't. This ends at when? 5 after the hour? Is that right? Okay, good. To get my congruences right. Whatever your mathematical style about chattiness or rigor or whatever, when it comes time to prove a theorem, please prove the theorem. Okay, what goes on outside of that can be very personal, but do prove it. Here's something else. I'm a little worried about running out of time, so I'll jump a little bit ahead here. People scan papers when they read them. Okay, so think of how you or a lot of people pick up a journal, thumb through it to see if they're interested. So they come upon a paper by XYZ, and they say, it looks like it might be interesting. Shall I read it or not? I wonder what the main results are. Okay, so you turn the pages a little more slowly as you go through that article, and you look for statements of theorems. What are the theorems that are being proved in there, or what are the points that are being highlighted, or whatever? Now, if the article is entirely discursive, and it does not have any summaries of any kind in it, then you cannot scan it and pick out whether the thing interests you or not. A lot of articles are just discursive. Okay, they keep on discursing all the way through, and it's hard to scan if it's a long article, particularly. So I guess I'm urging you to summarize your results using some bold-faced type or something. Get it right up there and turn on a special color of neon lights when it comes to summarizing. Do summarize it every few pages. What have you said? Put it up there as a proposition, as a theorem, as a principle of human behavior. as meaning of life, whatever, call it the meaning of life, bold-faced, and set it right there. Then somebody who flips the pages to see what you're talking about can look at that and then decide whether they want to read further or not. Also, for the same reason, here's something that's often overlooked. Here is how you might say you might state a theorem. Okay, suppose you're convinced of the truth of what I just said, and in your paper you will definitely summarize and state theorems. Okay, so here you come with main theorem, one of the main theorems, theorem 6. Theorem 6 might say this. Okay, I've seen a lot of papers like that. Now, of course, these things have been defined somewhere in the paper. If you look back 3 or 4 pages, you'll find the definition of this and the definition of this. Probably, if the paper is written this way, the definition of these two things will contain further terms that will send you chasing back some more pages in the paper to find out their definitions, etc. It turns out, though, of course, look, this is a subset of that, so what the fellow is really saying is that every one of these is one of those, and it would be really nice if this whole thing were reworded saying every weakly separable metrizable metric space is subcompactly embeddable in a star domain. Okay? Because that's what he's saying. He's saying that every one of these is one of those. Well, come right out and say it. So when it comes time to state your theorems, don't use just think of the person who is scanning your article as well as the person who is reading it from beginning to end. Because in order to get the second thing to happen, you have got to get through the first one successfully, more than likely. Okay? So think of the person who's scanning, and so try to drop the various notational abbreviations that you may have introduced. When it comes time to state the theorem, use as plain English as you can possibly muster up. Okay. Sir?
Yeah, something that goes along with that and what you were saying before about a catchy first paragraph.
Okay.
A lot of people try to cram their entire paper into the abstract when they write an abstract.
This is true.
And it's the same thing. The abstract is there. The person who's skimming may actually read the whole abstract. And you have to use that to hook them into reading the paper for you. It's a grand opportunity for that.
The abstract, if there is an abstract in the journal that you're reading, it's an excellent opportunity. I was thinking, certainly in the Journal of Algorithms, we have abstracts. In the American Mathematical Monthly, we don't have abstracts. So you've got to do it in the first paragraph or two, get somebody's attention. But yes, the abstract is certainly another chance that is being offered to you to get your main results up in lights in plain English to attract, or at least to inform readers about what they will be getting if they read your article, for sure.
I've got a question about that theorem. Not about that. No, not about that theorem, but about writing the theorem. If you put them in plain English, and then you want to go and prove them, do you say, well, the such and such sets correspond to this symbol, and the other thing corresponds to that symbol, or you just start in with the symbols and hope that the reader can grasp which symbol meant which thing, or how do you go from being sort of informal to being formal?
Well, you might, okay, that's a nice question. I'm not sure I have. You might say, if, as before, we denote such and such by C sub R M, and if we let the metrizable ones be D M R, then, if, as we did before, you might use something like that to smooth the transition. It could be a problem.
Somehow it just seems like the theorems are less precise if you don't put them in your formal notation. It just
okay. No, that's okay. Then mix them both. Say every, whatever I said before, semi-linear metrizable space XRM is a subspace of so-and-so. And so say the words and the symbols at the same time if you feel comfortable that way. That's okay. But somehow just think of the poor guy who's scanning the paper to decide whether to read it. You can quintuple your readership if you will let them in on what it is you are doing. And if they can really pick that up from scanning the paper, that's a big plus. Okay, it's kind of a string search operation, the scanning thing. Yeah, okay, so now under motivation, okay, so I think we could probably all agree that a little motivation is good, like saying where you're coming from, how you got interested in the problem, what you can do with it, that kind of thing is really nice. If there's a step in your argumentation that seems artificial, then often one feels that one ought to smooth that out a little bit. And a little bit, that's okay. That is, if there's an unmotivated kind of really quite artificial step sitting there, we get a guilt complex. We're teaching a class of students, and you can't just... the tip-off is a phrase like, consider the following, okay? What consider the following means is, here comes something from the left field bleachers, all right? It's just something you're writing down because it does what you want it to do and no other reason, okay? And of course you get questions after class like, where did you get that? And I said, oh, it's easy. It gave me the right answer. That's where I got it. I got it out of the book. And the real question is, where did the first person who ever got that idea get that? That's the real question, and that's the one I can't answer. I don't know. But anyway, so a little motivation is good, and even showing some simple approaches that didn't work, well, one or two of those are okay. But if you show a whole lot of them, then people are sort of itching to get on with it. Okay, so let's see what does work. And okay, I'm psyched up. Maybe you're going to show me something a little artificial, but it's okay. I don't mind. Just show me something artificial, but let's get this proof over with. All right. So little motivation, just a couple of sprinkles. That's nice. But that's much better than zero. But again, that has its limits also. Here is, for example, to show you one of the forms. I mean, motivation can take so many forms. Here is one of them, which I think is kind of an interesting. This is here's the, let's have a look at the paper. So this is a paper that has been accepted for publication in the American Mathematical Monthly. It's Ramanujan Modular Equations and Approximations to Pi, or How to Compute 1 Billion Digits of Pi, should you be desirous of doing so, by Borwein and Borwein Brothers of Halifax, Nova Scotia. Among the motivations that they use, let's look at sum 1 here. Sum 1, due to Ramanujan, is one of the many remarkable things that have come to us through that great man's brain. And let's just read it. It says that the square root of 8 divided by 9801 times the sum from n equals 0 to infinity of the factorial of 4n divided by the fourth power of n factorial, bracket 1103 plus 26,390n, all divided by 396 to the 4n, is equal to 1 over pi. Would you believe that? So that's in the category of a super dazzler. It's just it's stupefying super dazzler. And a thing like that is really good motivation. Where did it come from? How did he ever think of that? Well, you won't find the answer to how did he ever think of it. You almost never find out answers to that. I was just feeding the baby and the idea occurred to me. Okay, is the answer you get if you push it very hard. Well, but if you're feeding the baby and you get ideas like this, I mean, that's really, yeah, right, absolutely. Okay. This is really good motivation. This is not your standard kind of motivation that you would use in a mathematical article, but it is motivation. People tend to want to know where the dazzlers come from. Okay, they really do. So, okay. Yeah, let me look at the handouts that I prepared. I thought I should leave you with something tangible. What I have done here is to write up the very same subject in two completely different ways. Okay? Or that's what I was trying to do, anyway. What I'm talking about is how to count necklaces. Okay, you should have two handouts. One of them is 3 pages, one of them is 4 pages and is called Counting Necklaces, and the other of which is 0.6 pages, and it is called Enumeration of Orbits of Mappings Under Action of Cn, the cyclic group. Now you will recognize that as a thickly disguised version of this one, title, right away. They're both about counting them. They're both about exactly the same subject, right? I have written one of them in a pretty compact style. Okay, this one that goes through 0.6 pages contains a phrase like evidently up here. It contains a since clearly that's sitting over there. And it follows from simple manipulations sitting there. The other 4-page article over here contains none of those. What is evident in the right-hand one is 3/4 of a page here. What is since clearly here is another half page there. And what is the simple manipulations here occupy the whole last page of the 4-page thing. So I have expanded it. It's got pictures of necklaces with beads and all the colors and stuff sitting on the full write-up. There are pictures of necklaces here. And there's a very detailed description of the bijection that establishes one of these evidentlies, and there's a very detailed computation here with tossing around, playing games with the Mobius function and Mobius inversion, and double sums over divisor functions and stuff. It's really kind of nice. There's some terrible puns. I took the opportunity to put in some awful puns into, particularly on page 3. You can see that I'm really proud of them, and they don't appear in the in the censored version, which is the shorter one. And they both get the same answer. And I guess I wanted to show you like two sides of the coin here, okay? And I'm very definitely not saying to you that this is a better way and that's a worse way. I'm certainly not saying that. I'm saying these are two different ways to handle this particular problem as a rating problem. And you might want to run it through your own CPU personally and ask yourself, what is in each one of these that you would think would be good, and what do you think is bad or not so good. But it's important to remember that there are a lot of people in the world that like to work things out for themselves. And when they see a then evidently, it's okay. Not only doesn't bother them, they're happy. They take out a piece of paper out of their notebook and they work it out until it's evident. And then they go back to read. And they see simple manipulations. That's fun. That looks like that's going to occupy my commute to work tomorrow morning. So you take out the pad and you do those simple manipulations and you get off at your subway stop and you've had a nice ride. And so a lot of people, sorry? Subway, no, I sure am not California, that's for sure. Okay, I'm betraying my origins. Anyhow, so there are a lot of people that don't like to have things explained in too great detail. It really takes a lot of the fun out of it, and so on and so forth. As editor of the monthly, I get letters from people who, for example, I have gotten a couple of letters from people who say they don't like the chatty style in some of the articles. They wish it would be more formal. I had a letter a few days ago from someone who said just that, and who continued by saying that mathematics is basically a serious pursuit, and it's not a comic pursuit. Okay? And he found, when reading articles that had little jokes tossed in them, that the jokes took his mind off of the subject matter. And then he had to worry in the future about whether the next thing was intended to be a joke or was serious. And that just complicates an already complicated task of wondering where the epsilon over 3m's come from. And he was objecting, okay? And so there's no question of right or wrong there either. It's just that there are a lot of people out there who prefer their mathematics to be formal, and when they want to read something chatty, will buy a newspaper. Okay, it's a lot of people, and they have to be respected. There are a lot of points of view out there that need to be respected. So these are two possible ways to write the thing up. I noticed that when I wrote the longer one up, the 4-page counting necklaces thing, that I still hadn't said everything. There's still a few evidentlies left in there. So there's like a tree full of evidentlies, and there are no leaves in the tree at all. Every time you look at one, it branches off into 2 more computations. So there's a lot to say. On the other hand, it is in the category of something that a lot of people would want to work out for themselves and wouldn't particularly like you to have explained in such detail. On the other hand, there are loads of people, particularly people who are newcomers to the subject matter, that love to have pictures and to see the beads and see exactly what's meant by a necklace when you draw pictures. Then you know what a necklace is. And when you talk about 2 necklaces being different and show actual pictures of them, then that's very helpful. So I guess I just was hoping that you would run these 2 things past your own set of values, whatever they are, and see what you might try to learn from them. Comments, ma'am?
Actually, my question is about using first person. I noticed that one of the papers you showed us used first person. How do you feel about first person in formal exposition? I'm
in favor of it. We are in favor of it. Your present instructor is strongly in favor of using the first person. That took me a number of years. I should say took. It sounds like I've eventually reached the truth. That isn't what I was trying to say. But I've gotten to my present attitude on that after a number of years. And it's just that all the others seem so forced that I would rather just say I. I have found that this approach works, and just write it that way. So I use lots of I's. I try not to use too many, but I use lots of I's quite freely and unashamedly, proudly even, when I write. But that's one man's opinion. Okay, well, thank you very much. I've enjoyed being here.
Phoenix did. Legal advice here. I want to have people realize.
This analogy of